This is a pretty fun problem that serves to remind us that magnetic force is just another force. And so once you've found a magnetic force, you can use it just like any other force. And so magnetism, just like all the other units in physics, doesn't exist by itself. We're actually going to use magnetic forces in the context of other situations like kinematics or circular motion and so forth. So let's read this problem. A particle enters a B field with a speed of 140 meters per second and follows the path shown. Is the particle positively or negatively charged? Question A. And question B, determine the mass. Now question B might seem strange at first. How would we get the mass out of that? And this is how this problem shows us a connection back to previous units. So we'll take a look at that in a second. To determine if the particle is positive or negative, we'll need to do the right-hand rule with where the particle comes in at and which way the magnetic field is facing. Now there's a problem with this slide that I'm noticing. I think it got messed up on the computer, somehow switching to my iPad. So the charge starts down here, and it follows this path. So the little quarter of a circle. It does not go down these things. Particle comes in from down here, so this is its initial velocity. And then it follows the path that I kind of outlined in blue there, that quarter circle. So let's see if the right-hand rule would give us a force toward the center of that circle. Because in this case, if the particle came in from the bottom, to get it to go in that circle, we'd have to have a force this way. And so if the right-hand rule gives us a force that way, we'll know it was positive, because the right-hand rule applies to positives. If it gives us a force the other way, so if our force turned out to be that way, we would know it was negative, because a negative will get a force opposite what the right-hand rule gives you. Alright, so let's try it. We have V coming in from the bottom, so velocity up, cross B out of the page. My thumb points to the right, meaning we should have gotten a force to the right. Now, that's my way of doing the right-hand rule, the one I showed you. The one that's hard to mess up, I'll do it that way as well. So we've got V up, we've got B out of the page, so now my middle finger is pointing toward me out of the page, and my thumb points over that way. So that means our force should be that way, which is the same thing I got with my right-hand rule, V cross B that way. So V cross B that way. But in the picture of the problem, we know there's a force the other way because we're going in a circle, and so there has to be a centripetal force that way. And so if it's opposite what you get from the right-hand rule, that means we're dealing with a negative. That could be a little weird because in the video you're looking at the mirror version of me, so you may want to try this on your own with your own right hand, because it's kind of like you're looking at me in the mirror, and so that could have been a little confusing because you're like, wait, he said right, but maybe he pointed left. I'm kind of confused now. So try that yourself and see if you got the same thing I did. Okay, hopefully you've confirmed that the charge is a negative because it's got a force opposite the right-hand rule. Here's the part that I think a lot of students on the AP exam might see and go, whoa, I don't see how that's connected. Determine the mass. Well, I know there's a force here, and I know that force is related to mass by F net equals ma. So right now I'm thinking backwards. I'm thinking all the ways that force could relate to mass. I also noticed that this is a quarter circle, meaning we're getting a centripetal force for our F net, and so I can rewrite this centripetal force. And then the formula for centripetal force, mv squared over r. Now that looks like something that could be handy because the problem gives me a velocity, and it looks like it's given me a radius right here. And so mv squared over r I think I can use. My question would be, though, is that velocity staying the same? And the answer is no, actually, because the particle is constantly changing directions. Down here it's velocity straight up, then here it's that way, then here it's that way, then here it's that way. So it's constantly changing velocity. But in this equation, because this doesn't have the v doesn't have a little vector symbol over it like that. Instead, we've got this. That means we're just talking about the magnitude of velocity or the speed. And a centripetal force, a constant centripetal force, that is, wouldn't change the speed. Now, if this was like a up and down circle where I'm swinging a ball in my head around my head, and we've got gravity changing whether it's an in or out force, that's where things can get a little weird with velocity changing. But in this case, we know by the fact that the force is given by a cross product, QV cross B, that the force will always be perpendicular, and Q shouldn't change. There's nothing there to change the magnitude of V, and there's nothing to change the magnitude of B. So we should have a constant centripetal force, and we should have a constant speed. Now, even if you didn't think through all that logic, you could say, wait, well, velocity, not exactly sure what to do here, but I bet I could plug it in there, and you'd be right. So let's try it. Let's do Fc equals mv squared over r. We need to know the velocity, check. We need to know the radius, check. And we need to know the strength of the force, which we don't know. We can find the strength of that force, though, by using force equals. And if the velocity and magnetic field are always at right angles, then QV cross B just gives us, in this case, QVB. So in that case, our centripetal force is QVB, and I can do that. QVB equals mv squared over r. Now this is, you're about to see what you were shown in the video yesterday made by the other person. I can simplify this a bit, get rid of v, one of these v's. Now I've got QB equals mv over r. And if I want to know the mass, I just solve for the mass, so I get m by itself, multiply by r, and I've got r QB, I divide by v equals m. And now I just plug in the numbers. So if I bring that down here where I've got a little more room, I've got 960 meters times 8.2 times 10 to the negative fourth coulombs times 0.48 Teslas divided by 140 meters per second. When I do out that math, I get the mass of the particle is 0.00 and around about 27 kilograms, or 2.7 times 10 times 10 to the negative third kilograms. And so notice all I did was say, oh, there's a centripetal force here given by QVB, and that centripetal force should always be QVB because your force will always be at a right angle to your motion. If you have a particle moving in a circle in a magnetic field, you know from the cross product that your force is always perpendicular to your velocity. So QVB equals mv squared over r, and then I solved for m, and we've got it. All right, that's all. Hopefully this example made sense. Last night's video contains a shortened version of this example, so if you want to hit the highlights, you could rewatch last night's video, which was only about 3 minutes long. All right, that's all. See you tomorrow.